This is section 19 of the ACT Math Manual. Section 19 deals with functions. Now we have in a previous video dealt with quadratics, which is obviously a type of function. This is where we generalize a little bit more to all different sorts of functions and some of the more basic concepts and facts related to functions. Some of this stuff might be very simple for certain students. Some other stuff might be quite difficult, either because you haven't seen it in a while or haven't dealt with it, or had maybe not such a great teacher in school, or maybe you didn't pay attention in school. Who knows? But either way, functions are very, very commonly tested in tons of different ways on the ACT. So this is going to be a fairly thorough review of most of the stuff you're going to need to know how to handle for the ACT. So we are indeed going to start with the very basics of functions, which will include both the definition of what a function is, as well as some of the more common notation that you're going to see on functions questions. You'll need to be comfortable with all of this stuff. So first of all, in terms of what a function is, I like to start with a quick example. Again, if this stuff is obvious to you, obviously you can speed up the video if you would like. So if I were selling some product, let's call them widgets, because I'm not creative enough to come up with a specific product right now. So let's say I'm selling widgets, and in order to set up my company to sell these widgets, I have to invest, let's say $5,000. So I start $5,000 in the hole. I have given in $5,000, which means I am down $5,000. And then let's say each widget, let's say they cost, I'm going to sell them for $5, and I'm going to say the number of widgets is W. So I could model my profits by coming up with an expression. I could say, well, if I'm going to sell W widgets and they're $5 a piece, then the money I'm going to bring in is 5 times W, or 5W. But I have to remember, I always have to take out that initial $5,000 because that's what I invested. So my profit is a function of the number of widgets that I sell, and I can represent my profit by saying that if I'm given a number of widgets, I multiply that number of widgets by 5, that's where this 5W comes from, and I subtract 5,000, and that will give me my profit. So for instance, if I do really horribly and I only sell, let's say 2 widgets, so let's say W equals 2, then my profit, oh God, I'm going to be really in the hole. My profit is going to be 5, I'm going to do this in the calculator just so we don't make any careless mistakes, 5 times the number of widgets, which I said was 2, and I have to take away that initial $5,000 because that was my investment, that's what I'm in the hole, and I'm going to end up with negative 4990 in profit. So I am going to owe some people some money. Now, of course, if I sell, let's say 10,000 widgets, then I do 5 times 10,000, and wow, I've made $50,000, and now I have to take out that initial 5,000, and I have made $45,000. Not too bad, unless of course I made that over, a decade or two, in which case I should probably find a different business to go into. But the point is that this is what functions do. Functions serve as models for some relationship between 2 quantities, or 3 or 4 quantities, however many quantities you want. In this case, we have the relationship between P, which is profit, and W, which is number of widgets, and this equation, this function equation right here, is telling me that my profit is a function of, or depends on, how many widgets I sell, and I can find out what my profit is going to be by simply plugging the number of widgets that I sell into this equation, and I will get my profit. So that's a little bit of a background on what functions are and what functions do. Functions generally will have three parts, three components to them. They will have an input, which is the thing that goes in our previous example, that was the number of widgets. They will have the function itself, which basically will be telling us what to do to the input. In our previous example, we needed to multiply the input by 5 and then subtract 5,000 from that product, from that 5W. And then the output, which is the value that results. In our previous example, you may remember that that was our profit, our P of X. The more general or more standard letters and symbols in a function question are X, F, and F of X. So you'll need to be familiar with those, and you'll need to understand how, if ACT gives you different variables or different symbols, you'll need to understand how they relate to the typical symbols, the X, the F, and the F of X. So as another quick example, this one should be pretty simple. If ACT were to give you this function, if they were to say that F of X is some function that depends on X, and that function is represented by 2x plus 1, what they're telling you is they're giving you instructions. They're basically saying whatever x is, whatever's in this parentheses over here, you're going to want to multiply that by 2, and you're going to want to add 1 to that product. So not too dissimilar from the example we had given with our widgets business before. So input is x. Let's say that they tell you that the x equals 3. So basically what that means is we no longer have an x in the parentheses here. We have a 3 in the parentheses, and we multiply that 3 by 2 as the directions tell us to do. 2 times 3 is 6. 6 plus 1 equals 7. And we have our value of f of x, or f of 3. So our input was 3. 3 went into the function, and our output was 7. 7 came out of the function. Now, how functions will usually be presented? They will usually be presented, again, with those three parts we just discussed. You will usually get the function name, and by the way, they can use any letter for a function name. The most common are F, G, and H, but again, if you get a question that's discussing profit, you might see something like a capital P representing a function. So the function will be represented by whatever variable ACT chooses, or I should say whatever letter ACT chooses, because that actually is not a variable. And then they will have the definition of the function. They will tell you what the function directs you to do with the input. This function right here is telling us to square the input, then multiply that by 7, then add 3 to that whole term. And the definition will include the input, which is the thing in parentheses. And remember, that does not have to be an x. You may see something like g of a equals 7a squared plus 3. All of these are changing, and ACT can pretty much use whatever the heck they want to represent these different components of the function. So you will have the input, which is the thing in parentheses, and then you will have the output, which is not only this entire expression on the left, but also the entire expression on the right. As you can see, those two things are equal to each other. So the f of x and the 7x squared plus 3 are equivalent to each other. One huge point that most students understand, but I have seen students make careless mistakes because they don't understand this. This expression, f of x, these two things, the f and the x, these are not separable. This is one single entity, and the f and the x cannot be separated from each other, which means that if you see something like f of x equals blah, 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 this is not really an equation in the I guess truest sense of an equation. In other words, you cannot divide both sides of this equation by f to cancel those f's. You can't divide by x to cancel those x. You cannot do this. So if you see f of x, those things are inseparable. That is one single entity. Do not divide by f or x thinking that you can cancel one of those two letters, as you normally can do when you see two items side by side, like a 3x or even an x. You know, these expressions, yes, you can divide by 3 or divide by m to try to cancel some stuff, but you cannot do that with f of x. Moving along, the next page, which is page 144, 19.2, how functions will be tested. Again, functions are tested in a huge variety of ways, a panoply of ways, if you will, on the ACT. The most common, possibly, and definitely one of the simplest ways that ACT can test functions is they can give you an input and require you to figure out what the output is based on that input. And in order to do this, this is just a substitution type of question where you're basically plugging the input, which is the thing in parentheses after the F, you're plugging that input anywhere you see an X on the other side of the equal sign. So for example 1, if you want to go ahead and do this one on your own, you can pause the video, and I'm going to start it right now. One of the things that you do need to know about input to output questions is that ACT will spice these questions up by throwing in some exponents or some negatives, and that can lead to some trickiness because if you're not being careful about your order of operations, or if you are not aware that, for instance, I'm going to actually do this in 2 ways. The first way, I'm going to go ahead and write this in a slightly different way because let me get rid of that. So I'm going to write this with parentheses and dashes or spaces so that you can see that basically whatever is in this position, whatever is in this space, needs to go in these spaces here. So they are now telling me that in that space between parentheses is a -4. So I'm going to throw in a -4 there and a -4 there. And what I end up getting is 6 times -4 squared, which is positive 16, minus 2 times -4, which is -8. So this is 6 times 16 minus -8, which is 6 times 16 plus 8, and 6 times 16, again, not to waste any brain power, I'm going to go in my calculator, I'm going to do 6 times 16, that's going to equal 96. So this is 96 plus 8, which is going to equal 104. Again, I'm going to check that in the calculator just to make sure that I'm not making any careless mistakes, and I'm not. So this is 104. So that is how you would do this example. And if you made a mistake, for instance, by doing something wrong with your negatives or with your exponents, then you need to brush up on some of your algebraic skills. Now, there is one other way to do this, and we had actually talked about this in an earlier video, I believe possibly the Vita video. We could actually store -4. So I'm hitting -4 and then the store button, which brings up this little arrow on the screen. I'm hitting the store button, and then I'm going to hit X and hit enter. Now what I have done is I have stored the -4 in this X button. So X, anytime I hit X now and hit enter, it's going to be -4. So if I were to do 2X, the calculator will do 2 times -4 and give me -8. So now what I can do is I can actually just enter this entire expression into my calculator with the X's and all. I can do 6x squared, and notice I'm just entering this exactly as it appears on the page in front of me, minus 2x, and when I hit enter, boom, I get the 104. And that makes it a little bit easier, or at least makes it a little less likely that I'm going to make a careless mistake. If I enter this into the calculator the way that I just did, I most likely will not make a careless mistake as long as I'm entering everything exactly as it appears on the page. So that is another way you can handle a question like example 1. With multiple inputs, you will see some functions questions on the ACT that have multiple inputs. In other words, that have 2 or even 3 variables in the parentheses after the function letter. So when this happens, you're not really doing anything different. Now you're just substituting, instead of substituting one thing into the function, you're substituting 2 things. So go ahead, if you want to try example 2 on your own, pause the video. I'm going to do it right now, obviously. So we need the value of g of x comma y when y equals 3 over x cubed and x equals 2. So first things first, we need to be able to see that there is a substitution that needs to be done here. We have x equals 2 and then y is defined in terms of that x value. So we have to take that 2 and we have to plug it in here. So I'm going to do that first. Y equals 3 over 2 cubed, sorry. And again, I'm going to do this in the calculator so I don't make any careless mistakes. So 3 divided by 2. Now, remember, I need to hit enter and then cube the result, because if I hit a cube right now, it's going to apply the cube only to the 2. So I will hit enter and then I will cube that, and I get 3.375. So y equals 3.375. An alternate way to make sure you don't make a careless mistake when you do something like that, you can do alpha F1, bring up this fraction menu, hit 1, do 3 over 2, hit to the right, and then cube the entire thing. To be even safer, you might even want to put the 3/2 in parentheses, but this indeed, 27 divided by 8, did give us the correct answer. That's the 3.375. 3.375 and 27/8 are equivalent. So yeah, you do have to be careful of your order of operations. Just, you know, make sure you put the parentheses around the 3/2 or hit enter in the calculator before cubing the fraction value. So now I have my x and my y value. So this g of x comma y becomes g of 2, which was my x value, 3.375. So that was my x, that was my y. So now what I need to do is I need to plug the 2 and the 3.375 in wherever I see an x and a y respectively on the right hand side. So I'm going to do 3 times 2 plus 8 times the 3.375. Let me get that calculator out of there. 375 in parentheses, and I'm going to do this all right in my calculator. 3 times 2 plus 8 times, and actually I'm just going to enter that with the parentheses, 3.375, and I get 33. That is the value of g of xy when x equals 2 and y equals the 3.375. So again, all you're doing is dealing with multiple inputs, but you're doing the same thing that you were doing when you were dealing with a single input, just plugging in, substituting. Now, function of a function, composite functions. Some of you may remember notation that perhaps looked like, in math class, you might have seen notation that looked like F and then a little symbol that looked like an O, or even GOF. Those were the same thing as we're going to talk about right now. Those were composition of functions, where basically what ends up happening is, instead of just having an x in the parentheses as your input, you're going to have another entire function as your input. Do not get intimidated by these, please. These are not difficult questions. Yes, they look a little bit intimidating. Yes, they can require a lot of attention to detail and step-by-step work, but they are not difficult questions. Usually all you need to do on these questions, and this is written in this box right here, all you need to do is do these one step at a time, where basically you determine what the value of g of x is first, and then you plug that value, whatever you found for g of x, which frequently will be a number, sometimes it will be algebraic or variable in nature, but you'll just need to plug that number into the f function and then apply the f function to that number, or plug that number into the f function to get your answer. So down here in number 3, again, if you want to do it on your own, pause the video and take a stab at it. So they are asking for value of f of g of negative 3 when f of x equals 2x plus 10 and g of x equals 3x squared. So what I'm going to do first is what I set up here. I'm going to do this in 2 separate steps. first I'm going to do the g function. So I have g of -3 equals 3 times -3 squared. Well, remember, -3 squared is 9. 9 times 3 is 27. So I have just determined that g of -3 equals 27. Remember what I said up here. You now take that number and you plug it in for the input of the other, in this case, f function. So we do f of 27. Remember, we had f of g of -3. We determined g of -3 to be 27. So we are now just substituting that 27 in parentheses where there had been a g of -3. We now know what g of -3 equals. It equals 27, so that 27 is going in. Now remember, that has to go in for the f function. So f of 27 equals, now we're plugging the 27 in for our x in the f function. Our x in the f function was here. So this is, I'm sorry, our x, that was right. So 2 times 27 plus 10 is going to be 54 plus 10, which is 64, and we're done. So again, composition of functions or function of a function questions, you want to do them one step at a time, and as long as you do, they shouldn't be too difficult. Now, in the widgets example that we had discussed, we talked a little bit about how that function served as a model for our profit, and very frequently on the ACT they will test functions as models, and this will only be when the functions are very beautiful, because only beautiful functions can be models. Just kidding, we can all be models in our own way. Functions as models questions, very common on the ACT. They will look like the examples below. We're going to go ahead and do these. If you want to pause the video and try them on your own, perfectly fine. So let's take a look at number 4. The approximate number of students enrolled in Eastside High each calendar year can be modeled by the function s of t equals 600 times 1.1 to the t, where t equals 0 corresponds to the 2005 calendar year. Using this model, how many students will be enrolled in 2008? Okay, so first things first, let's make sure we understand what this part means. T0 corresponds to the 2005 year. So basically what that means is so let's do this just so you can see this visually. T equals 0, the year is 2005. T equals 1, the year is 2006. T equals 2, it's 2007, and t equals 3, it's 2008. So because they're asking for 2008, we're going to be using this value of t as our input in this function. So basically now what we have is s of 3, that was our t value, equals, and remember on the right hand side we are just plugging in, this is just a substitution, we're plugging in that 3 value because that was the thing in parentheses, that was the t, and we had a t up here in our exponent, so the 3 is just going in for the t, and we are going to absolutely 100% do this in the calculator. So this is going to be 600, and I can just enter this exactly as it appears, 1.1 in parentheses to the third. That was my t value, and I have 798.6 students. Obviously a student lost about 40% of himself, but that's okay. They said approximately, so the answer on this question would either be something like 798 or 799 or possibly even 800. So yes, that's the exact answer. Now, so that was just a substitution, just a plain old substitution. Some of these modeling questions, you'll have to go from output to input. We've talked a couple times about input to output, but on these modeling questions, sometimes they will tell us what results, and we need to figure out what number went into the function in order to produce that result. So in example 5, if you want to try it on your own, pause the video. Number 5, example 5, the height of an object thrown vertically from a height of 30 feet can be modeled by h of t equals -10t squared plus 20t plus 30, where h is the height in feet and t is the time in seconds. Using this model, how many seconds will it take the object to reach a height of 40 feet? So seconds to reach height of 40 feet. So that's what they are asking here. Now, I will say this type of question is going to be very difficult for a lot of students. If you have taken physics, it might look a little bit familiar because this should remind you of parabolic motion. Remember, this is a quadratic, so its graph would be a parabola, and if you've dealt with physics, you might have dealt with projectile motion or parabolic motion. So this might look a little bit familiar. You might have done some examples like this, but for the purposes of the ACT math, what you need to know is this. They are telling you that the height is 40 feet. And remember, in this model, in this function, the height is over here. The height is represented by h of t. What this says is that your height is a function of the time that you are that you have thrown the object, and t would be the time after throwing it. So 1 second would be 1 second, or what t equals 1, pardon me, t equals 1 would be 1 second after throwing, t equals 2 would be 2 seconds after throwing, and the height of the object will depend upon the number of seconds after throwing. Now, just as one quick example, you can see that at a time of 0, okay, when t equals 0, that means you have not thrown the object. Well, look what this all becomes over here. It becomes negative 10t squared, which is 0 squared, plus 20t, which is 20 times 0. Let me put these all in parentheses, plus 30. And these two go away because they're both zeros, and we get 30. And indeed, that's what the question had told us. The height of an object thrown vertically from a height of 30 feet can be modeled by blah, blah, blah. So when our time is 0, in other words, before we have thrown the object, we are at 30 feet. And that makes sense because that's exactly what the question said. I'm just giving you that example so you can get some sense of what's going on here. But now back to this 40 feet. This is the output. This 40 feet tells us that our h of t equals 40. And remember, that also equals this expression on the right hand side of the equal sign. So what do we have now? Again, we have a quadratic. We have some kind of parabola here. In order to solve quadratics, what do? We factor. We get everything to one side, making the other side 0. So I'm going to do that. I'm going to take this 40. I'm going to take this 40 away from the constant because those are the like terms. I am going to end up with negative 10t squared plus 20t minus 10 equals 0. And then I factor. Now, again, I've said this in the quadratic section. There are many ways to factor this. If you do have the type of calculator that can do this for you, I would recommend just using the calculator to do it. And in this calculator, again, it's in the apps, the polynomial simultaneous equation solver, which would be number 2 right here. It might not be number 2 in your calculator. You'll have to search for it. Your calculator may have more apps than this one. So I'm going to do polynomial root finder. I want to find my zeros here. This is a degree or order 2. I do want my complex solutions, if there are any, fraction, normal, float, degree, all fine. So I'm going to hit the next button, which is this graph key. This next tab corresponds to this graph key. The coefficients are going to be negative 10 and 20, positive 20 for the second coefficient, and then my constant is this guy here, negative 10. So I'm going to enter negative 10, and I'm going to hit the graph key, which is my solve tab. So solve graph, I'm going to hit that, and what I get is I get 1. I get that my t value, actually it's a double root, so my t value equals 1. So what that tells me is that at 1 second, I will reach a height of 40 feet. And indeed, I can confirm that by taking this 1 and plugging it back in for my t's. Let's actually see what happens. This is going to be negative 10 times 1 squared, which is just 1, so I'm not even going to write that, plus the 20 times 1, which is just 20, so I'm not going to write that, plus 30, and negative 10 plus 20 is 10, 10 plus 30 is indeed 40, which is what I needed. So it confirms that t equals 1 is the number of seconds at which I will reach 40 feet. Now again, if you had other ways to factor this and you wanted to use those ways, that's fine. I'm not going to go through them right now. If you have questions on how you would factor this without the calculator, you can either do a little bit of Google searching, or if you're working with a tutor, ask your tutor. Example 6. Maria is organizing a bake sale and will donate all profits to her local youth center. Wow, that is so generous, so magnanimous. The profit, P dollars, from the bake sale is modeled by P equals -50 plus 2B, where B is the number of baked goods sold. What is the minimum? So minimum number of baked goods she needs to sell so that she can donate at least $300. So notice the notation is a little bit different here. The symbology is a little bit different. They did not do a P of B, but that's fine. The P is just the P of B. We can see that the profit is a function of the number of baked goods. So this P and this P of B are exactly the same. The P actually makes things perhaps a little bit clearer than the P of B. So what we're going to do here is we need to know when this expression will be greater than or equal to the 300. We need the minimum number of baked goods so that she can donate at least $300. So this is really just a translation. This is -50 plus 2.5b. Sorry, 2.5. Let me get rid of that. 2.5b. Okay, I don't know what that was. 2.5b. That has to, we could just set it equal to $300. That would be fine and perhaps even a little bit easier. What I'm going to do is I'm going to say that has to be greater than or equal to 300. She needs to make at least $300, and at least in mathematical symbols is greater than or equal to. And now this is just a very basic inequality. So I'm going to add the 50 to each side, plus 50 plus 50. I'm going to get 2.5b equals 350. Sorry, I changed that to an equal sign. I should stay consistent. Then I'm going to divide by 2.5, and I'm going to get, let me clear this out of here. I am going to get 350 divided by 2.5, and that is going to equal 140. So what that tells me is that if she sells 140 baked goods, she will make that $300. And indeed, I could check this by taking the 140, plugging it back in for B, and then adding to it the -50, and I would see that that would give me $300. So she needs to sell 140 baked goods in order to donate at least $300. So she'll be up baking all night. So next one little note. This is actually an important / comforting note, or should be a comforting note here. On a lot of these questions, like the ones that we just did, these functions as models questions, there will be numbers in the answer choices. So if you have already done the NITIS section of the manual, you know that when there's numbers in the answers and the question is asking us for a single specific thing. So on this question, notice they're just asking us for what B would have to equal. So if there were numbers in the answer choices, we could take those numbers, plug them in for B into this expression, and find out which one gave us that $300 mark, or hit that $300 mark. So you could use NITIS on a question like this, and on a lot of the model questions. Now, in terms of split functions, not going to spend too much time on this concept because it does not show up very often on the test. And when it does, it's usually very simple as long as you're paying attention to details and reading the question carefully. Sometimes they will split a function into two different functions depending upon what your input value is. So they might say, for instance, that when x is greater than 0, when x is positive, you use one function, and when x is less than 0 or is negative, you're going to change that function to something else. The only tricky part of these questions may be the fact that they'll give you a negative, and then you'll have some negatives in the function and some exponents. Now, for simplicity's sake, this would be another time where you would want to use the power of your calculator. I'm gonna do it both ways so that if you so we should have this circled, by the way. I'm gonna do this both ways so that you can see how it would be done both ways. So remember, -2 is obviously less than 0, so we're using this second function. I'm gonna do this first the way I did it before. Remember, I said that you can think of what's ever in parentheses as a blank, and then we have the thing in parentheses and blanks over here. So 2 times, let me get the calculator slightly out of the way here, 2 times the blank minus 15. So all I have done there is I've just replaced all of the x references with a set of parentheses and a blank, and now I'm going to fill in the -2, which is what they're asking me about, this -2. I'm going to fill that in all of these blanks. So let me actually go ahead and so that we don't get confused, I'm going to actually erase these blanks so they don't get confused with the negative. So -2, -2, -2. Now again, we just have to be very careful here. -2 cubed is -8. -8 is +8. And then -2 squared is +4, but we're subtracting that +4. And then this is 2 times -2, which is -4, but we're subtracting that -4, so that's +4. And then we are subtracting 15 at the end. So this is 8 minus 4, which is 4, plus 4, which is back up to 8, minus 15, which is 7. So our answer should be 7. Now, if we do this in the calculator, we're going to use that store function. We're going to do -2, we're going to hit store, and we're going to put it in this X key. And then what I'm going to do is I'm just going to type in this function as exactly as it appears. I'm not going to change anything. So I have a negative, then the X, then a cube, and then I am subtracting an X squared, and then I am subtracting a 2X, and then I am subtracting a 15. I just realized I made a mistake. That was supposed to be -7. That is my fault. See, you got to be careful. Even the best of us make mistakes. Yeah, so that should have been 8 minus 15, which is -7. And when I press enter here, hopefully I'll get the calculator to confirm that I was right. Yes, -7. I should say that I was right the second time. But either way, yeah, that should have been a -7. And yeah, that's the two ways you can do a question like that. Now, domain and range. Next page, page 146, domain and range. So first of all, let's talk about the definitions. The domain, you can think of the domain as your x values or all allowable inputs to a function. Again, also your x values. And the range is all allowable or possible outputs. Oops. These would be your y or f of x values. Calculator keeps getting in the way there. Your y or f of x values. So again, the domain is what goes in to the function. The range is what comes out of the function. Now, keep in mind there is one type of question that I want to differentiate from the term range when it comes to functions. You may also see the term range as it relates to range in in data sets. So by contrast, a range in a data set is actually the difference between the greatest value and the least value in the data set. So if you had something like 2 and 10 and 7 and -3, so your greatest value is the 10, that's the G. Your least value is the -3, so 10 minus -3. Your range here would be 13. So keep in mind, again, if you do see a range question, or you see the term range in a question that is dealing with averages or means or medians or any sort of statistical data set, the range means something slightly different in those questions. It's just the difference between the largest value and the smallest value. So back to ranges as they apply to functions, we have to talk about some things that need to be excluded from the domain and range. For those of you who have taken pre-calculus or calculus, you most likely dealt with these types of questions a lot and hopefully are fairly proficient with them. The first thing that we need to understand is if you have a rational function, in other words, if you have a function that has a numerator and a denominator, the denominator cannot equal 0, because remember, when a denominator equals 0, the fraction or the ratio is undefined. So if there is any value of x that will produce a value of 0 in the denominator, you have to exclude that value of x from your inputs, from your domain. The easiest way to do questions like this is to simply set your denominator equal to 0 and then solve for the variable, solve for the x. So when I solve for the x here, I add the 2, I get absolute value x minus 2 equals 2. Remember, in order to, if you've watched the absolute value video or done the section in the manual, you know that we have to split this up into two different equations. This would become x minus 2 equals 2, or x minus 2 equals -2. Get that out of the way again. Equals -2. And then we solve both of these. So plus 2 plus 2, so x equals 4, plus 2 plus 2, x equals 0. Both of these values, x equals 4, x equals 0, when they go into this position, we are going to produce a 0 in the denominator. 4 minus 2 is 2. Absolute value of 2 is 2, so that would be 2 minus 2, which would equal 0. And when 0 goes in, we have 0 minus 2, which is -2. Absolute value of -2 is 2. So again, 2 minus 2 is 0. So we have to exclude the 0 and the 4 from the domain. X cannot equal 4 or 0, or else this function will be undefined. Now, in example 2, same sort of thing. We are going to set this denominator equal to 0, and we are going to solve for x. Now, the easiest way to solve for x here, actually there's a couple of easy ways. I'm going to do it with factoring. So remember, this is a difference of squares. X squared minus 9 is a difference of squares. So I have my x's, which x is the square root of this first term. I have my 3's, which is the square root of the second term. And then I have 1 plus and 1 minus. So x minus 3, x plus 3 equals 0. The 0 corresponding to this factor would be x equals 3. The 0 corresponding to this factor would be x equals -3. So I get that x cannot equal 3 or -3 because both of those values will produce a 0 in that denominator. So I have to exclude these from my domain. Now, keep in mind, again, there's other ways to solve this x squared minus 9. There's ways to use the calculator. You can also add the 9 to both sides and you would get x squared equals 9. You do need to remember that when you square root a squared variable, you have to account for both the plus and the minus value. So other ways to figure out what x is here, I just did it with regular old quadratic factoring. Now, example 3, again, we're just because this has a variable, another variable in it rather than a number, doesn't mean we do this any other way, any different way. We just say x, a minus x equals 0. We solve for x, and the way that we solve for x is now by adding an x to each side. So we get a equals x or x equals a, which means x cannot equal a, and we can see very clearly that if x did equal a, we would have x minus x or a minus a in the denominator, both of which obviously would give us 0. So x cannot equal a would have to be excluded from the domain. Now, 59 at the bottom of this page. Which of the following linear equations gives the vertical asymptote for the graph of y equals 201x plus 202 over 203x plus 204 in the standard xy coordinate plane? So we need vertical asymptote. Now, you need to keep in mind that a vertical asymptote will occur at any values, and it's usually of x, of your input, that make the denominator equal 0. In other words, vertical asymptote is no different from what we just talked about. So for instance, in example 1, there would be a vertical asymptote at x equals 4 and x equals 0. So you would x equals 4 would be, let's say, out here. So you would have a vertical asymptote that the graph would never cross there, and then you would have a vertical asymptote at 0 that the graph would never cross there. And if we were to plot this, let's actually see what this would look like plotted. Some of you may be aware that you can actually enter, let's do 1 divided by, and I'm going to put the entire denominator in parentheses, 1 divided by, and then in my math menu, some of you might be aware, we have an absolute value function. So I'm going to use that here, obviously. So 1 divided by x minus 2, get out of the absolute value, and then subtract 2 end parentheses. So I've just entered this function into my graphing screen, and then I'm going to graph, and watch what's going to happen. Boom, boom. So notice I get a line on the y-axis, which, remember, that is the line x equals 0. The y-axis is the line x equals 0, and then I get a vertical line that my graph does not cross as well on at x equals 4, the vertical line x equals 4 here. So we can see from the graph that indeed we are getting vertical asymptotes that our graph cannot cross at both x equals 0, the y-axis, and x equals 4, this vertical line out here. So back to number 59, all we are doing here is trying to find the x value that will make this denominator equal to 0, and that will also give us the equation of the vertical asymptote. So I'm going to do what we did before. I'm going to set 203x plus 204 equal to 0. I'm going to subtract the 204, subtract the 204. I'm going to get 203x equals negative 204. I'm going to divide by 203, divide by 203. I'm going to get x equals negative 204 over 203. And I'm going to look for that in the answers, and I'm going to be very, very careful because these answers look a lot alike. This is 201. I needed a 204. I needed a 204. I needed a 204. There's a 204. And fortunately, D is the only answer with a 204 in the numerator, and that is my answer. So x equals negative 204 over 203 will cause the denominator to be equal to 0, so I have to exclude that value from my domain, and a vertical asymptote will also occur at that value. Now, vertical asymptote and number line holes, this is not all that commonly tested on the test. If you are going for a very high score, yes, you should know this stuff. If you are not going for something well into the 30s, you might not have to worry about too much of the stuff on this page. This stuff at the top and at the bottom is fairly rare and tends to show up only in the last few questions on the test. So vertical asymptotes and number line holes, you have to understand that a value that needs to be excluded from your domain or range will produce asymptotes, will produce either, as we said before, a vertical asymptote at the x value or a horizontal asymptote at the y value. there is a little bit of a difference between vertical and horizontal asymptotes that's a little bit beyond the scope of the ACT. For instance, one big difference between the two is that a graph can actually cross its horizontal asymptote, whereas a graph can never touch its vertical asymptote. Again, not so important that you understand that for this test. And if you're interested to know more about that, Google it. So an x value that makes the denominator equal to 0, we've already talked about the fact that it will create a vertical asymptote at that x value, but it will also create an open circle on a number line. So you might need to be able to look at a graph or a number line and work backwards. Instead of finding the x value and then determining where the vertical asymptote or hole would be, you might need to look at the graph and determine what x value is excluded from the domain. These should not be very difficult. You can see that this graph here approaches but does not touch the line at x equals 2. Again, from the left side, approaches but does not touch the line at x equals -2. So that would tell us that there is a vertical asymptote at x equals -2. It will also tell us that that -2 has to be excluded from the domain. So x cannot equal -2. The graph never touches x equals -2. In example 5, we should see, this one's even simpler, we should see that there is an open hole at -2 and 1. An open hole indicates that that value of x is not included in the domain of whatever function you're dealing with. So in this case, x could not be equal to -2 or 1. Pretty simple and straightforward. Now, horizontal asymptotes, these questions definitely are some of the most challenging for most students on the ACT, only because either students haven't learned this or it was not explained all that well to students, or again, you might have been sleeping in class when you learned about horizontal asymptotes. Wake up! So horizontal asymptotes occur at y or f of x values that are excluded from the range. Again, that's technically not completely accurate, because as I said before, a graph actually can touch its horizontal asymptote. Perhaps a better way, or I should say a more accurate way of defining a horizontal asymptote, horizontal asymptotes describe what happens to a function of a graph as x values get really big. So as a quick example, let's look at something like this. So if you had a graph that looked like this, let's say it almost looked like a sine or cosine function, but it was starting to, the crests and the troughs started to get less and less and less, and let's say this value in the middle was, I don't know, was 2. So we can see that as our x values get really, really big, as x approaches, maybe infinity, so as x approaches infinity, that's an ugly infinity symbol, sorry. As x approaches infinity, we can see that, yes, the graph has crossed that line y equals 2 several times. It has gone above and below it several times. But as x gets really, really big, our graph seems to be getting closer and closer to 2. So like I said, to define a horizontal asymptote, it's not actually values that have to be excluded from the range. It's what happens as x values get really, really big, really, really small. As one other example, you could take a parabola. Think about a parabola. So remember, parabolas just go up or down infinitely, right? This parabola would just keep going and going and going and going and going. It would never stop. So as our x values are getting bigger and bigger, as x is going to infinity, remember our y values are also just getting bigger and bigger. So here's an x value, x value, x value, x value, x value, y value, y value, y value, y value of this point, this point, this point, this point, this point, this point. Notice that our y values are getting bigger and bigger and bigger, and they don't stop, which means there is no horizontal asymptote here. There's no value at which y sort of levels out or starts to approach as x gets bigger and bigger and bigger. In this case, as x gets bigger and bigger and bigger, y also gets bigger and bigger and bigger. So there is no horizontal asymptote. Now listen, again, I'm racing through a lot of this stuff. If this is something that you are not solid on, and you are going for a very high math score, you're going to need to be more solid on it. So you're going to need to work with your tutor, or you need to going to go online and do more research. But like I said, am rushing through a lot of this stuff right now in the assumption that most of you perhaps still remember a lot of this information and just need a little bit of a refresher. So how do we deal with horizontal asymptotes on the ACT? We're going to go ahead and write down a bunch of stuff here. So you may have, or you may remember that in school you might have learned something about top heavy or bottom heavy functions. So first of all, you have to remember we're dealing here purely with rational functions. Okay, rational functions. And with rational functions, we've got both a numerator function, which I'll call g of x, and we have a denominator function like f of x. In other words, we have a function that's made up of both a numerator and a denominator. So this applies only to rational functions. If you just have a regular old quadratic like x squared plus 2x minus 3, or regular old linear function like 2x plus y, then you don't deal with asymptotes generally. But if you were to put the quadratic in the numerator and the linear in the denominator, then you have a rational function and you have to worry about asymptotes, both vertical and horizontal asymptotes. This should not have been 2x plus y. I don't know why the hell I wrote that. Let's change this into a 4. Oh, now it works. 2x plus 4. So the way that you do this is if you have a top heavy rational function. And what does that mean? That means that the degree in the numerator is higher than the degree in the denominator. So this all deals with degrees. Remember that degree means the highest exponent on your x value in your function. So for instance, if I had x cubed over x, let's say x plus 2 and x cubed plus x squared minus 2x plus 3. So this would be known as a top heavy function, where we have a degree in the numerator that is higher than, remember there's a 1 on this x, that is higher than the degree in the denominator. When that happens, when we have a top heavy rational function, we have no horizontal asymptote. No horizontal asymptote. So top heavy functions, no horizontal asymptote. I apologize, I'm going to run out of room here. We'll just write at the bottom of the page. If we have a bottom heavy rational function where the numerator degree is lower than the denominator, so we could just take the reciprocal of this. I'll make up a new one. Let's do 2x minus 3 all over, let's do 3x to the 4th plus, let's keep it simple, plus 7. So here we have a linear function, a degree of 1, over a quadratic function, a degree of 4. When this happens, there is a horizontal asymptote, and this is always true, horizontal asymptote at x equals 0, which is also, sorry, that is not correct. That is not correct. Let me get rid of that x. That was my fault. At y equals 0, and that is otherwise known as the x-axis. The line y equals 0 is the x-axis. It is the horizontal line that is the same as the x-axis. So again, bottom heavy means you have a horizontal asymptote on the x-axis. And then the final scenario is if you have equal weight or equal degrees. So, okay, that's digress. That's not even a word. So let's change that. So if you have equal degrees, so for instance, let's say you have both quadratic in the numerator, 3x squared plus 2x minus 7, and let's say you have another quadratic in the denominator. Let's say you have 4x squared minus 10. I don't know. If you have equal degrees, then you have a horizontal asymptote. Horizontal asymptote, let me get rid of this for a second. Horizontal asymptote at the ratio of the leading coefficients. Leading coefficients meaning the coefficients that are in front of the x term with the highest degree. So the x term with the highest degree again is the quadratic term here, the squared term. So you would have in this case a horizontal asymptote at y equals 3/4. 3/4 being the ratio of the leading coefficients. So 3/4 you would have an asymptote at 3/4. Now, just so you can see how this works with the calculator, because you actually can use your calculator for some questions like this. So I'm going to go ahead and I'm going to type in 3x squared plus 2x. I'm just typing in this function that I just gave, minus 7. I'm going to end parentheses there. I'm going to delete that. And I'm going to enter parentheses here. So insert parentheses. So there's my numerator. I'm going to divide this by parentheses 4x squared minus 10 and parentheses. Now when I graph this, some students are going to look at this and say, well, it doesn't look like there's any horizontal asymptote necessarily. It looks like this portion of the graph seems to go through all y values, and indeed it does. And remember what I said though, by the way, there does look to be some vertical asymptotes, which makes sense because if we make x certain values, we're going to produce zeros in the denominator. So that would be what we'd be dealing with vertical asymptotes. But again, you've got this portion of the graph that seems to run through all y values, which is why I said before we can't really think of horizontal asymptotes as things that the graph can't cross. We have to think of them as the horizontal lines that the graph gets closer and closer to as we go farther and farther to the right, or get bigger and bigger or smaller and smaller x values. And I'm going to show you how you would determine what the horizontal asymptote is here in a couple of different ways. One is I'm going to hit my trace button, which is right here. I'm going to hit trace, and if I go to the right and I just keep going, so notice my cursor right here, you'll see it moving farther and farther to the right. So as I move farther and farther to the right, you should see, and this obviously day of the test, you might not want to do it this way because it's going to take a long time, but you're going to see that y value. Notice this y value right here. It was really big and then it got to something like 0.8, and now it's getting smaller and smaller and smaller and smaller. And you would see if we kept going farther and farther to the right, it's going to start approaching, guess what value? That 3/4, that ratio of the coefficients. And yeah, you know what, let me zoom out here. Let me zoom out, and then I'm going to do the same thing. I'm going to start, oh, this calculator is slow. So go back to trace, and I'm going to start going to the right. And again, you can see I'm getting closer and closer to 0.75. And if I were to keep going, I'd start getting very, very, very close to 0.75, like 0.75000, blah, blah, blah. The other way that I can do this is I can always go to my table, which is second and then the graph key. And in table set here, I need to set this to, I want the calculator to ask me for my independent x value. Okay, remember the independent variable is my x variable. So I'm going to set the calculator to ask. I'm going to go back into my table, and now I'm going to type in a gigantic number for x, like 10,000, and guess what's going to pop up right here? Oh, there it is, 0.75, something really close. If I make very close to 0.75 or 3/4. If I make x even bigger, like I make it 100,000, I believe the calculator is probably going to just give me 0.75 because it, oh no, 0.75001. So you can see I am approaching, as x gets very, very large, I am approaching this y value of 0.75. And again, that is what a horizontal asymptote tells us. It tells us what happens to y as x gets very, very big. So hopefully that gives you some background on horizontal asymptotes. So now with number 60, we actually have a couple of different ways to do this. The easiest way is to use the information that I just gave you here about top heavy, bottom heavy, and equal numerators and denominators in our rational function. So notice that in this rational function, by the way, they are just asking us what the horizontal asymptote is. In this rational function, we have equal degrees in the numerators and denominators. The biggest exponent on x up in the numerator is 2, and the biggest exponent on x in the denominator is also 2. This is a 1 here, so this is the biggest denominator. So this is equal numerator and denominator. So remember what we said, the horizontal asymptote is going to be the ratio of the leading coefficients. Leading coefficient in the denominator is a 1, it's just not written. So the ratio of the leading coefficients is 2/1, and our horizontal asymptote will occur at y equals 2/1, which is Anne's choice K. That is probably the easiest way to do a question like this. Do keep in mind, however, if you understand what a horizontal asymptote is, you could have done this using the calculator by doing 2x squared minus 18. You put that all over the other function here, which you got to put in parentheses. So x squared minus 5x in parentheses. Hit the graph button. I'm going to hit on so that stops graphing. On will interrupt your graph if you want it to. I'm going to go back to Z standard, zoom standard, which is number 6. So I get the standard window. So again, notice from the graph screen itself, it is not obvious what y is approaching as x gets really big out here or x gets really small out here. So I'm going to do what I did before with the table. I'm going to go to second table or second graph. And notice my x values are already in here, and you can see that when x is 10,000, y is 2.001. When x is 100,000, y is 2.0001. Let's throw in one more x value, like a million. 1, 2, 3, 4, 5, 6. When x is a million, and there the calculator has finally run out of brains and just rounded to 2. So I can see that when x is really, really big, it's getting closer and closer to 2. So I could use my calculator in that way to find a horizontal asymptote if I was struggling. But again, I'd still have to have some idea of what a horizontal asymptote is. Hopefully that all made some sense. Now finally, sorry, not finally, we got a couple other things to do here. This is a lot of material. You want to stop, go get a glass of water, maybe a snack, pause the video, go ahead and get it. I'll wait. Okay, you're back. Cool. 19.3, function changes and effects on graphs. One of the things that you're going to need to know about is how graphs move when you make changes to them, or I should say how graphs move when you make changes to the function that the graph comes from. So there's a bunch of different things that you can do to a function that will make it move or even change shape on the XY coordinate plane. We're going to use a very simple quadratic, a very simple parabola to demonstrate these changes. So when we are dealing with our regular old function f of x, which like I said, we're going to do the regular old parabola, and I'm going to actually graph this as accurately as possible so we know exactly what this looks like. So 1, 1, 2, 4, negative 2, 4, and then I'll try the 3. 3, this is hard to do on a screen. So 3, 3, this guy was a little bit off. That should have been there rather than there. Let me get rid of that. There we go. So and then 0, 0, obviously. So our parabola, our regular old parabola looks, oh my God, looks something like, wow. Oh, okay, this is going horribly wrong here. Look, I tried, it didn't work. I'm just gonna do this. So our regular old parabola, look at that. Worked out so much better when I just didn't even think about it. A regular old parabola is going to look like that. So now what's going to happen when I start making some changes to this function? Well, what's going to happen is I'm going to notice that there's some changes being made to the graph. Now, by the way, we can confirm all of this stuff by using the calculator. I'm not going to use the calculator in these cases, but if you wanted to see how this stuff was causing the graph to change in your calculator, you could do that. Let's start our discussion of these changes that we can make to the graph by let's put a constant in front of our original equation. I'm sorry, in front of our original function. So our original function was this x squared. So what we're going to do is we're going to put a constant in front of that. So here's how this works. So we are putting a constant of a, where a is greater than 1, in front of our original function. So we're making a new function, g of x, where it is just 2 times the original function. We're putting a 2 in front of the original function. Remember that the original function was x squared, f of x was x squared, f of x was x squared. So this is now 2x squared. So our function g of x is 2x squared. Now, I'm going to try to do this, but it never works out very well on the screen. Let me choose a smaller guy here. Let's do something you're going to be able to see. Let's do this manually. My apologies. Let's do this. No, let's do, what the heck? There it is. Let's do a tiny little guy there. So let's try to think about what's happening here. So remember, the original function was 1, 1, 2, 4, and 3, 9. So 1, 1, that was negative 1, 1, and negative 2, 4. And this would be 1, 1, and 2, 4. Well, remember that putting a 2 in front of all of our x squared values, these were our x squared values. X squared was 1, x squared was 4, x squared was 1, x squared was 4. Those were our y values, or our x squared values, because y was equal to x squared. Well, remember, they're all going to double now. They're all going to become twice what they were before. So I'm going to do these in blue. So this guy's going to become 2, and this guy's going to become 2. For negative 2, we're now going to get 8, and for positive 2, we're now going to get 8. So what's going to happen to the graph is it's going to get, it's not too bad, a little ugly, but whatever. It's going to get skinnier. It's going to get slimmer. Another way of saying that is it's going to get steeper. And actually, if you think of what happens when you do this with a linear equation, like y equals x plus 2 to y equals 2x plus 2, well, that number in front of the x is your slope. So in this first equation, it's a slope of 1, and in the second equation, it's a slope of 2. So the line just gets steeper in the same way that your parabola will get steeper when you give it a bigger slope. Parabolas don't technically have slopes or constant slopes, but we can think of this the same way. That number in front of the x is going to be our steepness factor or our skinniness factor. So the change on the graph is going to be graph gets skinnier or steeper or thinner. Now another situation is you could put a constant in front of the function, but that constant could be between 0 and 1. In other words, it could be fractional. If this happens, I'm not going to try to do this the nice way, but if this happens, your graph's going to get wider or fatter or less steep. So graph gets wider or less steep. Okay, so that is a coefficient of a fractional coefficient between 0 and 1. Now, if you put a negative coefficient in front of the function, then what that's going to do is that's going to flip the graph upside down. In this case, it's going to reflect it across the x-axis. So flips graph upside down. You can remember the negative makes the graph upset. It changes it from a smile to a frown. Next, we could add a constant to our original function. We could take our f of x and we could add a constant to it. What that is going to do is it's going to increase all of the original y values. Remember, the original y values again were x squared. It's going to increase all of those original y values by 2. So instead of a 1, we're going to have a 3. Instead of a 0, yeah, that's correct. Instead of a 1, we're going to have a 3. Instead of a 0, we're going to have a 2. And instead of the 1 over here, we're going to have a 3. So basically what has happened is, man, that's tough. Basically what has happened is we have actually shifted our graph up 2 units. So when we add that constant, we shift the graph up 2 units. The shape stays the same, even though it doesn't look like it from my drawing. The shape stays the same, but we just take the graph and we translate it up 2 units. So we're going to go ahead and write down shifts graph up, and we're going to say k units because k is what we had used to represent the constant that we're adding. So we shift graph up k units. If we subtract a value, well, that just does the sort of the opposite of what we just talked about. So let's say our k in this case is 3. We're subtracting the 3. That shifts the graph down 3. So it would start, instead of at 0, 0, it would start at negative at 0, -3. So the shape of the graph wouldn't change, even though my drawing makes it look like it does. This would shift graph down k units. Shift graph down k units. So that's what happens if we add or subtract a constant to the function. Now, what happens if we don't add a constant or subtract a constant to the function itself? What happens if we add a constant to the x in the function? In other words, to the input of the original function. So this is the difference between taking the original function and adding a value, and taking the original function and adding a value to the input of that function. This situation we just dealt with up in example 3. This is a new situation. Some of you remember this well, but basically if you add a constant in parentheses, in other words, add a constant to the input itself, you will shift the graph 4, in this case 4 to the left. So you will have a parabola out here. You went from 0, 0 to a vertex of 0, -4. So you shift the graph to the left by 4. So you shift graph left h units. So you're going to shift the graph left h units, and then if you subtract in parentheses, you subtract from the input, from the x, you're going to shift the graph right h units. So this guy, you're subtracting 3, that's going to shift the graph to the right h units. So, wow, man, that's bad. Hopefully you were able to draw this stuff more neatly on your paper than I'm able to do on the screen. There's not a lot of delicateness here on this with this setup. So again, you've got to know how the changes to the original function are going to affect the graph, whether the changes will make the graph skinnier or fatter or flip it upside down or shift it up, down, left, right. You need to just, basically, you should probably just have these memorized. If you want to know the reasons that all of these things happened, I tried to give you some sense in a couple cases of why this stuff happens. But if you want to know the reasons, again, it's going to require a little bit more work with your tutor or some searching online on your own. So let's take a look at a type of question that is testing the stuff we just went over. The graph of the equation h equals negative at squared plus bt plus c, which describes how the height of a hit baseball changes over time, is shown below. So this guy's showing, okay, so I guess that's the arc that the baseball is following. If you alter only this equation's c term, which gives the height at time t equals 0, the alteration has an effect on which of the following? Oh, sorry. If you alter only this equation's c term, which gives the height at time t equals 0, the alteration has an effect on which of the following? So effect on which? So they are saying that when you throw in t equals 0, time equals 0, you get the height at time equals 0. And that makes sense because, again, if you throw in 0, this term goes away, this term goes away. So that would leave us with c. So this point right here is 0 comma c. In other words, that's our y-intercept. Now what they are saying is we are altering the equation's c term. Now what that would look like relative to, I'm going to write h of t because height is a function of t. What would that look like relative to the stuff that we just discussed is this. We would have our original function, which is negative at squared plus bt plus c, and then we would be adding or subtracting something to this c. So we would end up with negative at squared plus bt plus c, and then plus or minus some other number. Let's say it's an n or a 2. Let's actually just make it a number. So we would now, instead of having just plus c, we would have plus c plus 2, and that would be the same as h of t plus 2, right? Because this is all h of t, and then this is a plus 2. I'm just focusing on the plus right now. So it would be h of t plus 2. So what are we doing? We are just adding a constant to the h of t. In other words, it's something like h of t plus k, which is what we talked about on the previous page. It's one of the scenarios that we talked about. It was in scenario 3. H of t plus k. We're adding a constant or subtracting a constant from the original function. So I'm actually going to draw what this would look like. Remember what we said that does. It just shifts up or down our graph. It just shifts up or down our graph. So if we take this entire graph and we shift it up, it's going to look, I'm going to try to do this neatly. Ooh, look at that. That worked out pretty well. It's going to look something like this. If we shift this guy up, we're just going up, 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 up. It's going to look like this. So now we go to these answer choices. Well, let's look at this. The h-intercept. The h-intercept. Well, the h-intercept, yes, it's going to change. If I take the original function and I shift it up, the h-intercept is going to change. So 1 definitely is going to change, which means I can get rid of g and h because they don't include 1. The maximum value of h, well, the maximum value was here, and that's going to shift up a couple. So yes, that is going to change, which means I need a Roman numeral 2 in my answer, which means I am done. The only answer that would work would be answer choice K, which is the only one that has a 1 and a 2. But we can also look at the t-intercept, which would be, in other words, the x-intercept. That would also change because my x-intercept would move from here to over here, which I can see after having drawn the new graph. So all three of those are going to change if I add a constant to my function. It's going to shift the function up, and all three of those parameters are going to change. Weird symbol or new operations. These guys are very closely related to functions. They pretty much require the same skills as functions. So let's go through these. So you may on the ACT every now and then you're going to encounter some weird symbol like these dots right here, these dots right here, or this sort of bullseye looking thing right here. You have to understand, like I just said, that these are pretty much the same thing as functions. When they give you something like upside down black triangle x, which I'll just call function x, when they say function x, you could also call it weird symbol x, they tell you weird symbol x is defined as x times x plus 1. That is exactly the same as saying that f of x equals x plus 1. In other words, if you had an upside down triangle and then a 2, what they are telling you to do is to take the thing next to the upside down triangle and throw that in for your x's. Same thing over here. If you had f of 2, they are telling you to throw that thing in for your x's. So it's getting ugly. So you're talking about exactly the same thing here. It's just substitution. That's basically it. So examples 1 through 4, I would go ahead and try these guys on your own before watching me do them. I'm going to go ahead and start working through them right now. So this is weird symbol 7 or upside down triangle 7. Well, remember what this means. This means take the 7 and throw it in everywhere that we see an x for this original function, for this function here. So this is going to be 7 times 7 plus 1, which is 7 times 8, which equals, I believe, 56. At least it used to. They might have changed it. I'm not sure. 7 times 8 equals 56. Now, weird symbol a just means we're now taking an a and plugging that in for our x. So this is going to be a times a plus 1. If you want to distribute the a, you can. You get a squared plus a. That's all we can do there because we don't know what a is. So that's just an algebraic solution. This is a composite weird symbol function. So note here we have the upside down black triangle 2. So what does that mean? Let's do the thing in parentheses first. We'll do order of operations. So upside down triangle 2 means, let me actually do this down here. So upside down black triangle, or red triangle now, 2 means 2 times 2 plus 1. I'm just plugging that 2 in wherever I see an x over here. So that's 2 times 3, so that equals 6. So now this upside down triangle 2 is now 6. That's what I just found here. And now I'm going to apply my outside triangle. So I'm going to do upside down black triangle 6, and that's going to be 6 times 6 plus 1, which is 6 times 7, which equals 42. So I did the inside weird symbol function first, and then I applied the outside weird symbol function to that inside one. Now, upside down black triangle or weird symbol n equals 6. So notice what they're doing here. Here, they're not giving me the input. They're telling me that they are giving me the input, but it's a variable. I don't know what that input is, but they're telling me that when that variable goes into this weird symbol function, I get out a 6. So in other words, what they're telling me is there's a missing piece here. Upside down black triangle n would be n times n plus 1, and they're telling me that that equals 6. So this is going to be n, I'm going to do this over here, times n plus 1 equals 6. I'm going to distribute the n. I'm going to get n squared plus n, and I'm going to subtract this 6 over here. And now what do I have? I have a quadratic. I have an ax squared plus bx plus c equals 0. It's a quadratic equation. I can solve this through factoring. Remember, there's other ways to do this. You could also use your calculator. So this is going to be n and n. I need a plus and a minus. I'm going to have a positive 3 and a negative 2. When I FOIL that, it's going to give me back this n squared plus n minus 6. So my n values that make this equation true, my roots, are going to be negative 3 and positive 2. And indeed, if I throw in either of those values for my x's here, like for instance 2, I get 2 times 2 plus 1. Well, remember, that does equal 6, which is what they told me it had to equal. If I throw in negative 3 times negative 3 plus 1, that's negative 3 times negative 2, which also equals 6. So I have checked and verified that the negative 3 and the 2 work. That is the background on weird symbol functions. You may see stuff like number 19 on the test. Let's go ahead and do this one. If you want to try it on your own, press pause and come back and join us after you think you have gotten it. So for all positive integers a, let function A, I'm just going to say function A, or you could also say weird symbol A. Let function A be defined as the sum of the digits of A multiplied by the number of digits in A. For example, blah, blah, blah. They give me an example. So they want the value of function 314, weird symbol 314. So again, we have to pay attention to this. Sum of the digits of A multiplied by number of digits in A. So in the example, you can see the sum of the digits is 3 plus 1. This is a digit, this is a digit. We add those to get the sum, and then we multiply by the number of digits. There are 2 digits, so we're multiplying by 2. Well, in this case, the sum of the digits is 3 plus 1 plus 4, and the number of digits is 3. So we're just doing 3 plus 1 plus 4, which is 8, times 3, which is 24. An intimidating looking question for some students, but very simple if you don't get intimidated. Weird symbols with multiple variables. Weird symbols with multiple variables. You will see some weird symbol question functions that have multiple variables. They can, again, sometimes look intimidating. Try not to get intimidated because they're not that difficult. Now, what you want to do with these questions is this hint right here, and I'm going to show you what it looks like in number 17, because if I just say it, it's not going to make any sense. So for all integers c and d, let the operation whatever be defined by c whatever d equals d squared plus 2c. So they're defining the weird symbol there by saying that whatever is here goes in here, whatever is here goes in here. Fine. We square that thing, we add it to 2 times that thing, and so on and so forth. So they want the value of this. So there's 2 sort of tricky things going on here. One, this is a composite function. Notice that this 2 function 3 is the thing to the left of the symbol, of the weird symbol. So that 2 function 3 is actually the c. So c is being defined in terms of another whole function. So we're going to have to do this in order of operations. We're going to have to do this stuff first, and then we're going to have to do this second operation. But before we even do that, I want to address this hint here. Write what variable the number corresponds to. So how does that apply here? The way it applies is this 2 is a c value, and this 3 is a d value. Remember, the thing to the left was a c, the thing to the right was a d. So this 2 is a c, and this 3 is a d. I'm not going to worry about this 4 yet, because I need to do the thing in parentheses first. But that's what I mean by writing the variable that the number corresponds to. So now your eyes have a very easy way of, when you're calculating this expression, they have a very easy way of seeing that the c is the 2 and the d is the 3. So remember, we just said the c is the 2 and the d is the 3. So the d right here is getting squared, and then the c is being multiplied by this 2. So this is 9 plus 4, which equals 13. So now I know that all this stuff on the left is 13. So now I have 13, and then this weird symbol. I have 13, 4. So now I just have another weird symbol function to calculate, and now I have a new c and the d from the original function. So now I am going to do the d squared, which is 16. It's 4 squared. Okay, d squared, that's the 4. 4 squared is 16. Plus 2 times the c plus 2 times 13. And this is going to equal 16 plus 2 times 13. I'm going to do that in the calculator, which is over here off screen. Let me get out of here. 216 plus 2 times 13 is 16 plus 26, so it should be 42, but I'm going to confirm, yes, it is 42, and indeed that's what they were asking us for, this stuff up here, so we are done. So again, I would write down what the variable correspondence is. The 2 corresponds to the c, the 3 to the d, and then in the new function, the 13 corresponds to the c and the 4 to the d. Now, finally, other rarely tested functions concepts. Sometimes ACT will ask you a question very clearly and often simply about the degree of a function and what that degree corresponds to in terms of naming convention. So this function right here, hopefully you recognize that there is a 1 exponent on this x, that means this is a degree of 1. Remember, degree corresponds to the highest exponent on your x term. So if you have y equals x something, so y to the first equals x something, the degree is this guy in here. So this would be a degree of 1. That is known as a linear function, and a linear function always has that's not right. Always has 1, 0. Linear function can only intersect the x-axis or have an x-intercept one time. That's easy to see. If you draw a line, boom, there's your intercept. There's no way a line can have any more zeros than that. This guy is a degree of 2. It is known as a quadratic. When you graph a quadratic, we've talked about this several times, you get a parabola. Parabolas can have up to they can have 2 zeros. Those 2 zeros can either be real or unreal, but all parabolas will have 2 zeros. This is a degree of 3. It is called a cubic, and the total number of zeros can be 3. And that, again, can be a combination of real and imaginary, or real and complex zeros. So that's degree of a function. Even and odd functions, I would not worry too much about this, especially if you are not headed for a score into the 30s, well into the 30s. If you are headed for that score, you are going to need to know about this. So easiest way to deal with even and odd functions is with symmetry. So basically all even functions are symmetric with respect to the y-axis. What does that mean? That means you can take the function, you can split it or fold it along the y-axis, this vertical line, and the two halves will match up to each other. So you can see in a parabola that yes, a parabola that has its vertex on the y-axis will be symmetric with respect to that axis. Now, not all parabolas are even or are symmetric with respect to the y-axis. For instance, this parabola over here, that's obviously not symmetric with respect to the y-axis. It is symmetric with respect to this line that runs through its vertex, but is not symmetric with respect to the y-axis. So basically, if you have a parabola whose vertex is on the y-axis, then yes, that parabola is an even function and is symmetric with respect to the y-axis. Now, an odd function, so this guy over here is even. An odd function is symmetric with respect to the origin. Now, symmetry with respect to the origin is a little bit tricky to understand, but basically if you take the graph and you rotate it 180 degrees around the origin, so in this case I can look at this piece of the graph. I can see that if I rotate this guy, well, if I rotate it 90 degrees, it would end up there, and if I rotate it 180 degrees, it would end up here. So this graph indeed is symmetric with respect to the origin. I can rotate this graph 180 degrees about the origin, and I will get the same graph, or the two halves of the graph will match up to each other. Again, this stuff is a little bit tough to see, especially when you're not sitting in front of a tutor or a teacher, which means that, as I've said many times before, you may have to talk to your tutor about this in a little bit more detail, or get some clarification from the web, some more clarification. So this is an odd function. This is symmetric with respect to the origin. So in this third example here, it should be pretty clear to see that this is not an even function, because here's my y-axis, and this thing obviously is not symmetric with respect to the y-axis. If I just consider this piece on the right, reflecting that over the y-axis would look like this. So I can see that the graph does not match up with itself on the other side, on the left side of the y-axis. So obviously it's not symmetric with respect to the y-axis. Now, in terms of determining whether this is symmetric with respect to the origin, in other words, in terms of determining whether this is odd, it's very difficult to envision what this would look like when rotated about the origin. So I'm actually not going to do that right here. I'm going to actually use the definition of an odd function. The definition of an odd function says that if you have a point x, y on the graph, then the point negative x comma negative y must also be on that graph. And we can actually go back to this second example and see sort of what that means. Let's pretend that this point here is, let's just pretend it's 1 comma 2. Okay, it's close enough. So what the definition of an odd function says is that if 1, 2 is on the graph, then the point negative 1, negative 2 must also be on the graph. And indeed, look down here, we have the point approximately negative 1, negative 2. Let's look at, I don't know, let's look at this point here, and let's pretend that point is 2 comma 1, 2, 3, 4, 5, 2 comma 5. So in an odd function, negative 2, negative 5 must also be on the graph. And indeed, if we go down here, bam, we have the point negative 2, negative 5. So over here in this question, we can, I don't know, let's just even look at, where's one that's sort of there. So this point, let's pretend that it is 2 comma 1, 2, 3, 2 comma 3. Well, remember, by definition, in an odd function, if 2, 3 is on the graph, then negative 2, negative 3 should be on the graph. So negative 2, negative 3 is down here. Well, that's not on the graph of this, which means this is neither even nor odd. Increasing, decreasing functions. Now, increasing, decreasing functions, what this means is we're trying to figure out what is happening to the y values as our x values increase. So here's our x values, here's our x values. What is happening to the y values as our x values increase? So let's consider this parabola in two pieces. Let's consider the x and y values from point A to point B, and then we'll consider the x and y values from point B to point C. So as I move from A to B, as my x values get bigger, what's happening to my y values? They are actually getting smaller and smaller and smaller until they bottom out at point B. So this graph is decreasing on this interval from this x value to this x value, and it is increasing on this interval. This graph right here, again, we're going to consider this in two pieces, from point A to point B, and then point B to point C. And we can see that over both of these intervals, the graph is increasing. Now, obviously, there is a point here where the graph levels out, but the graph never stops increasing. It certainly never decreases. So we're going, as our x values increase from left to right, our y values are always increasing, and same thing over here. As we increase our x values from left to right, our y values are going up. This guy over here has several different segments where it is doing different things. So as our x values are going left to right, y values are increasing here, then they stop increasing, and then they decrease in the middle, and then they increase over here on the right. So that's what increasing and decreasing is all about. Inverse functions show up very rarely on the ACT. First of all, you do need to know that the notation for an inverse function is this. So if you ever see f negative 1 of x, you should keep in mind that this negative 1, when it is in function notation, it does not mean the same thing as when you see it just above a variable. This is an exponent and indicates a reciprocal. This negative 1 is our notation in functions that indicates we have an inverse. And inverse and reciprocals, they are not the same thing at all. So don't make that mistake. So again, when you see f to the negative 1 of x, we're talking about inverses. Here's how we would do a question like this. So they are asking us what f of negative 1 is for this function. There is a very simple process that you can go through to make these questions very easy. Step number 1, you want to change the f of x to y. So this f of x, we're going to make it a y. So I'm going to do y equals 2x squared minus 3. Step number 2, we swap the x and the y. Now, again, if you want explanation as to why we're doing this or what exactly an inverse is, you're going to need to talk to your tutor or do some research on your own. I am doing this simply to show you what the process is and to show you that if you do get an inverse question on the ACT, they generally aren't too bad. So step 2, like I said, I swapped the x and the y, and then step 3 is I solve for this new y. So I need to add the 3 to both sides. I get x plus 3 equals 2y squared. I then divide by 2, I get y squared equals x plus 3 over 2, and then to get the y completely alone, I do square root of both sides and I get y equals, remember I have to take the positive and negative when I take the square root of a squared variable, so this is plus 3 over 2. And then if you want to include a fourth step, you just change the new y, the y that you solve for, back to the notation that they had given you. So f negative 1 of x, inverse of f of x, in other words, equals this guy up here, and that is actually our final answer. So the inverse of this function would be plus or minus x plus 3 over 2. That would be f negative 1 of x. That is it for functions. I guess I shouldn't say that is it, because that was a lot of material. But look, if you want to do well on the ACT, you are going to need to make sure that you are very solid with understanding functions. This has already been a very long video, so I'm not going to do a recap. Make sure you go back and review this stuff. As I've said probably 10 times already, there might be some of this stuff that you need more review on, more help on, more explanation on, and if that is the case, you have got to either do it on your own, or if you are working with a tutor, make sure you get the explanation that you need from your tutor.